Just give it a second. All right. Today we're going to be continuing real analysis and talking about bounds. So in the topology metric spaces video, we introduced the notion of boundedness in a metric space, right? Which was that a set is bounded essentially if the metric between any 2 points in that set is less than some finite distance, right? Now, what we can do in the real numbers is, since we have more than just a metric, we have an order, right? So we can introduce upper and lower bounds. So this is something we're going to define. M is an upper bound, which I'm just going to, well, I'll write it out first, I guess, but I'm going to be abbreviating it a lot. Is an upper bound for A, which is a subset of the real numbers. This means that for all A in the set A, the element A is less than or equal to M, right? So we allow the possibility that M might be a, say, maximal element, right? M might be in the set, and it's still an upper bound as long as it's greater than or equal to all of the other elements. And so similar definition for lower bound as well, right? And for bound, I'm going to be abbreviating it as BD. Now what we're going to do is define what's called a least upper bound. So a least upper bound L, or I'll say, let me rewrite this. I'll say L is a least upper bound if, and I'll specify for A some subset of the real numbers, if it is an upper bound and if L prime is any number less than L, L prime is not, I should emphasize, not an upper bound for A. And so that's where we get this least upper bound, right? If anything is less than it, it is not an upper bound, and therefore it is the least upper bound. And the rest of this video is going to be essentially concerned with constructing this least upper bound, right? And in particular, when does it exist? So this is going to be the first sort of deep theorem that we will encounter, is that if S is some non-empty set, so this is a subset of the reals, if this set has an upper bound, then the least upper, or I should say, I guess then n, or a least upper bound or no, it is the, I guess by construction it's unique, is the least upper bound, then the least upper bound exists. So the rest of this video will be concerned with the proof of this theorem, because it's kind of not trivial. So the first thing right off the bat is that we're going to be using our first sort of preposition that S is non-empty. So we're going to let little s be some arbitrary element of big S, right? Now let A1 be any number less than S, right? Which obviously is going to exist. And let B1 be an upper bound for S, big S, right? Our set S, which we know exists by hypothesis, right? We said that our set has an upper bound, so we're letting B1 be an upper bound, right? So now we're going to place it in sort of a dummy variable. We're going to want to consider the average A1 plus B1 over 2. We're going to break this up into two cases. If X is an upper bound for S, let A2 equal A1 and B2 equal X. Otherwise, let A2 equal X and B2 equal B1. So let me draw this pictorially, right? We have our set, which is sort of going to be abstract. We don't really know how to represent our set, but we know how we have this little element S, right? And then we said let A1 is just some number less than S, and B1, I'll draw it over here, I guess, is an upper bound for S. What we're doing is we're considering this point X in the middle of A1 and B1, and we are asking, is X an upper bound? If X is an upper bound, then we replace, or then we set B2 equal to X, and then A2 equals A1, in which case we're going to consider this interval. Otherwise, if X is not an upper bound, which in this case, I guess it doesn't look like it is, so I won't say in that case, but otherwise you consider setting A2 equal to X and B2 equal to B1. So in either case, B2 is an upper bound. So, or I won't, but that's the important thing to note, is that B2 is an upper bound. And you essentially just repeat this process of what we would call interval halving for each integer, right? We just repeat it over and over again. And so we can see, right, the b's are always going to be, the way we're constructing this, the b elements, the b sub n, are always going to be upper bounds, right? Because in either case, right, if X is an upper bound, then the next b becomes x, which is an upper bound. Otherwise, you let it be the previous x, which was also an upper bound. So b sub n is always going to be an upper bound. Now, we can write explicitly the distance between b sub n and a sub n. It's going down by half each time, right? So we know this is going to be b sub 1 minus a sub 1, which, by the way, is positive. Really, we don't need these absolute value bars the way we're writing it here, because we know b sub n is going to be bigger than or equal to a sub n, but I'm going to write the absolute value bars anyway. Divided by 2 to the n minus 1, right? And you might be inclined to put 2 to the n here, but just make sure it works for n equals 1, for example. If n equals 1, then you have 2 to the 0, which is 1 here, and so it checks out. And you can easily prove, so check. You can easily prove that as n goes to infinity, this sequence, right, this is a sequence, is going to converge to 0, right? Therefore, then we're going to use the definition. We're going to break this limit into a definition. So let epsilon be greater than 0. Then is some natural number such that the distance between b sub n and a sub n is less than epsilon. And this just means that the length of the interval, right, remember our interval here would be a sub big N to b sub big N. This interval has a length which is less than epsilon. And since we are doing this interval halving, we also can notice that each interval is going to be contained in the next one, right? So if n is bigger than or equal to big N, we know that a sub n and b sub n are going to be contained in the interval a sub n, a sub big N, and a sub, b sub big N. Right, and you can sort of see this pictorially. Each time you construct a half interval, it's always going to be contained in the previous interval, and so I guess you could say by induction, you're always going to have subintervals. Then, right, so what was I saying? Then if, okay, so let me erase this. If n and m are bigger than or equal to greater, the bigger n, then let's say a sub n and a sub m are in a sub big N, and b sub little n and b sub big M are in a sub big N, b sub big N. And this implies if these elements are contained in this interval, which has length less than epsilon, then the length between them is less than epsilon. And again, we're sort of using a pictorial argument, but you can prove that, say, using the triangle inequality. Then the sequences A sub n and B sub n are Cauchy, so they converge. We're going to say A sub n converges to A, and B sub n converges to B. This is thanks to our completeness axiom in R. Now, since let's see, how should I say this? Now, since A sub n and B sub n were contained in A sub big N and B sub big N for all little n bigger than or equal to big N, A and B are also contained in this interval. And we sort of saw why this was true, I think, or am I thinking ahead of myself? But the reason this is true, by the way, is due to the fact that if you have some fixed number and you have some sequence, then you can prove that the limit must also, so if the sequence, if all the elements of the sequence are greater than or equal to x, or at least up to a certain point, you could argue, then the limit must also be bigger than or equal to x. And you can prove that by contradiction. If you assume a is less than x, then you can sort of take epsilon to be, say, x minus a, and then you would get, for some n big enough, you would get a sub n less than x, which is a contradiction. And I feel like we did that proof already, but or something like that, but I'm not sure. But you should go through the details yourself, of course. And so a sub, and so since a and b are in this interval, the distance between them is less than epsilon. And this is true for any greater than 0, right? Because a and b the construction of a and b did not rely on epsilon, right? We used epsilon to show that a sub n and a sub n and b sub n converge, right? But we're also using this epsilon, which was arbitrary, to show that the distance between a and b is less than epsilon. So a equals b, right? Because this is essentially just a formulation of a limit definition where the limit is 0. So really there's a minus 0 that we aren't seeing here. And we're showing that, really, we're showing that a sub a minus b converges to 0, but a minus b is constant. So if it's converging to 0 and it's constant, it must be equal to 0. And therefore a equals b. Thus let L equal a, which is also equal to b, right? We want to prove, we want to show L is the least upper bound for S. So we continue on to the next page, which coincidentally was the next page on my little notes. Now, remember little s was an arbitrary element of our set, right? And although we used a sub 1 we picked a sub 1 to be less than s, right? But at some point, the a could have surpassed the a could have surpassed s, right? So a and b, they don't really rely on what s is. So theoretically, we could say let s be an s again, but really it doesn't matter. We can use the same variable that we used before. So that's just something nitpicky. But anyway, so we're going to pick a random element, not random, but just an arbitrary element of s. We want to show first that L is an upper bound. So suppose, to the contrary, that S is bigger than L. So let epsilon be S minus L. Since B sub n converges to L for some n in the natural numbers, we have B sub big N minus L less than epsilon, right? But B sub big N minus L is less than or equal to its absolute value, which is true in general. X is always less than or equal to its absolute value. So B sub n minus L is less than epsilon, which is S minus L. So B sub n is less than S. However, B sub big N is an upper bound for S. So this is a contradiction. Thus, S is less than or equal to L for all S in L, or sorry, all S in S. So L is an upper bound. Now let L prime be less than L, and let epsilon be L minus L prime. Since A sub n converges to L, there is big N in N such that the distance between A sub n and L is less than epsilon. But L minus A sub n is less than or equal to A sub n minus L. And again, this is true in general. I could write minus x is less than or equal to the absolute value of x. That's true. So L minus A sub n is less than L minus L prime. So L prime is less than A sub n. Sorry. These should all be big N's. A sub big N. I got it. Okay. So, what it is that as we have defined it recursively, we have defined the A sub n's as not being upper bounds, right? Because when we define a sub 1, we said a sub 1 was less than s, right? So it's not an upper bound for the set big S, right? And for each iteration, if a stays the same, then we know it's not an upper bound. But so if a stays the same, then it's not an upper bound. But if a changes, if a sub n plus 1 equals a sub n, then we'll sort of work by induction, right? If a sub n equals a sub n plus 1 equals a sub n, then that means that a sub n plus b sub n over 2 is an upper bound, right? Because then this becomes b sub n plus 1. But if a sub n plus 1 changes, that means then a sub n plus 1 is a sub n plus b sub n over 2, which is not an upper bound, because that's why we're changing a, right? If this average is an upper bound, then it becomes a b, but if it's not an upper bound, it becomes an a. So all the a sub n are not upper bounds by induction. So when we let L prime be less than L, we're assuming this is an upper bound for S. So we're assuming L prime is an upper bound for S, which is less than L, and what we've shown here is that we have some a sub n, which is bigger than L prime, and if L prime is an upper bound, then that means a sub n is an upper bound. But we know that all the a sub n are not upper bounds. But all a sub n are not upper bounds. So L prime does not exist. Thus, L is the least upper bound. So I'm gonna just scratch that out. Not scratch it out, but cover it out. Yeah, I had a massive brain fart, and I'm going to edit that out of the video. And so that concludes the proof of this theorem. Now, the final minute or two of this video is just going to be introducing some notation. So if S has an upper bound, we denote the least upper bound as LUB of S. But there is a notation that you may have seen before, which is denoted as the supremum of S. So this is spelled out supremum. And this is defined piecewise. This is defined as the least upper bound of S if S has an upper bound. And this is defined as infinity otherwise. And remember in the last video, I believe, I mentioned that infinity is not a number, right? This is not an element of the real numbers. Rather, it is a symbol, or rather a notation that we use in conjunction with our order operation on R, right? Infinity just means that infinity is just some object which says that if I take any real number, it is going to be less than infinity. And so some other things to note are similar definitions are the greatest lower bound of S, and similarly with the supremum, we define the infimum of S as the GLB of S if S has a lower bound. And you should prove, just like we proved that a set has a greatest lower bound if it has a lower bound, we prove that a set has an least upper bound if it has an upper bound. You should also prove that it has a greatest lower bound if it has a lower bound. And you don't really have to, like, theoretically, you could just redo this proof with changing some inequality signs, but there's actually a slick way to do it. Now, this is equal to negative infinity otherwise. And negative infinity, similar to infinity, is just something where, I guess you would say, negative infinity is always less than an element of the real numbers. And so that is it for this video. Do you have any questions?
Oh, yeah.
All right, that's it.